Part 2, the crystal order. We start with the cloud modeling treatment of vapor deposition. Such models must simplify the crystal by assuming the crystal is a spheroid, or sometimes just a sphere. The models also use a capacitance analogy in which the vapor at the surface is assumed to be in equilibrium. That is, the total mass deposition to the crystal, the mass uptake, is simply calculated as that amount that diffuses from far away to this equilibrium region next to the crystal. As a result, properties of the ice surface have nothing to do with the mass uptake or the habit. So the habit is a complete mystery. So we'll get rid of this capacitance or equilibrium assumption. But first, see what it can do. This plot shows the mass uptake in grams after 3 minutes of growth at water saturation, that is in the cloud of droplets. Temperatures are cooler to the right. The dotted line here shows the case for the sphere in the capacitance analogy. It shows a peak at about minus 15. And the measurements follow this pretty well, also showing a peak near minus 15, although the peak is higher. After 10 minutes, the tabular or dendritic crystals are picking up speed here, and the peak gets larger, but also a new peak appears. The columns and needles are kicking in. So the mass uptake peaks are due to the habits, which are driven by the surface. Clearly, growth is being influenced by the surface, so let's look at the surface. Now, a growing crystal surface is not spheroidal. It is flat. That's what gives crystals their sparkle. Now, they are flat because they grow by layers. Here's how it works. Take this magnified view right here. So some molecule comes down from the vapor, hits the surface, bumbles along, and maybe it'll hop off, but some of them will reach this little edge here. This is the edge of an incomplete layer, also known as a step. And when it reaches that, it sticks. And so the boundary of this incomplete layer has moved a little bit. And as more and more molecules come down and stick there, the step sweeps across the surface. That is, the crystal gets thicker, it grows. This video shows thick layers spreading across basal surfaces. Look for their color changes, like here. Now, these layers get started because the crystal grows up against some other thicker crystal, or maybe against some fleck. But also note that some crystals, like this, don't thicken at all. And this one, they just grow laterally. But here's one where you can see the layer spreading. It's got started by this little fleck right there. But how do new layers start on freely falling crystals? They don't touch anything. This is crucial. Two ways in general, distinguished by the growth rates they produce. For growth promoted by defects over here on the left, growth is slow but steady at low supersaturation, but it rises steadily with supersaturation. This is also characterized as being highly variable. You see all these curves here? By the way, this type of plot, rate versus supersaturation, we use it a lot, so pay attention. Layers can also nucleate, like bubbles nucleating spontaneously when you open a beer or pop, but these are two-dimensional, and they're very regular. They're not sporadic. At very low supersaturations, growth is essentially zero. No layers nucleate until you reach S crit. This value depends on the type of face and on the temperature. Then above this value, layers nucleate rapidly, and the rate quickly reaches the limit. Now, both of these types may occur in snow, and with both, the defects will cause a little growth at the lowest supersaturation, but nucleation takes over at higher values. Now we deal with these higher supersaturation conditions here, so we focus on layer nucleation. Remember this, because this is high sensitivity to supersaturation, layers nucleate at corners. When the supersaturation is highest, S-crit is different for basal and prism, and for each face it depends on temperature. So, how does layer nucleation explain crystal habit? First, how does layer nucleation explain the tabular columnar transitions? This crystal here shows two transitions. First, it grew as a column, then it fell into a tabular regime, where it grew these plates or caps. Then it fell back into the columnar regime and grew a crown. So it's a crowned capped column. We start the beginning, a droplet, say, at minus 15 degrees C. The vapor is close to equilibrium with respect to liquid, but this is about 15% with respect to ice. And then the droplet freezes. It then sucks up the vapor nearby, and so the supersaturation at the surface drops. Back to the just formed crystal, and here we have our growth rate plot. The supersaturation at the corner is initially high, as marked here. You're up here on the curve, and here both faces are initially at their maximum rate. And so the supersaturation at the corner starts to drop, bringing it down to where the basal face is no longer nucleating at its maximum rate, and is now a faster rate on the prism. The supersaturation near the crystal continues to drop, its value at the corner dropping below the basal critical value. Though some growth may continue on the basal from defects, almost all of the growth is due to the prism. And the prism drops below its maximum rate, falling to the steep region here where the system can reach a balance. Now these S-critical values may differ by only 30% or so. The growth rates can differ by a factor of 100. This is highly asymmetric growth in the tabular regime. The tabular column transitions are then explained easily by temperature changes in the critical supersaturations. Like this case over here on the left, the tabular regime, say minus 15, the critical value for the prism is lower than that of the basal. But over here on the right, the columnar regime, the critical value for the basal is the lowest. And by the way, theory does predict that the temperature should change these critical supersaturations. Now this theory that I've just explained was first proposed by Charles Knight in 1972 and Sir Charles Frank independently in 1974. And they just argued along these lines that the extreme changes in the growth rates can only be explained by layer nucleation. So that's how things sat for a few decades. We had the strong theoretical argument I just mentioned. Also, Charles Frank argued that the crystal symmetry of dendrites requires layer nucleation, and Akira Yamashita pointed out that the branch straightness required it, but still there was no direct evidence. Now the video of layer spreading that I showed earlier showed basal faces that are apparently below their critical supersaturation, but experiments like those aren't useful for measurements of S-crit because of possible strain influences from the substrate and all those nearby crystals that make it hard to know the supersaturation. So in 1994, I was eager to start a new experiment without these issues. And with Charles Knight of NCAR, we came up with this device. The basic idea was to isolate the crystal from these other influences and have very sensitive control of temperature and supersaturation. Here are examples of what we could do and what we saw. We have here over on the left this ultra-thin glass capillary. It's only about 4 to 7 microns across. A droplet has just frozen. The faces are just being expressed. And we could track it as it grew, rotating it and looking at all the crystal faces. So I was content to examine cases like this, measuring their growth rates very carefully. But then something unexpected happened. Like down here on the left, I saw crystal faces that would stop growing. And I found this surprising because it meant that if I got below the critical supersaturation, there was absolutely no growth, meaning there's no defects. We had these relatively large crystal faces. I mean, in terms of molecular size, these are huge, but they are defect-free. And I found these critical supersaturations were very reproducible. So I thought, well, hey, that's what I'm going to study. So I started measuring S-crit, and here's what I found. Here are the critical supersaturations for both faces, and the coldest temperatures are down over here on the left. First of all, we found that the values, around 1%, are very low, much lower than theory predicts. The other thing was that the prism face, here in blue, was nearly independent of temperature, between about 0.4 and 0.5%. But on the other hand, the basal had a strange behavior. It started around 1%, around -1, and it dipped down really low to about 0.15%. Then at lower temperatures rises back up. In the dendrite regime, it's quite high, about 2.5%. So as Knight and Frank had argued, there are two crossing points, and these are at the tabular columnar transitions. So above -4, the prism S-crit is lower. Between about -4 and about -9 and -10, the basal S-crit is lower, and then below -9, -10, the prism is again lower. So, in short, experiment agrees with theory, but also we find that the real culprit here is the basal phase. This, I think, gives a more illuminating answer to Kepler's and my question as to why the dendrites are so thin and flat. Well, at that temperature, the basal faces cannot nucleate in new layers, so they don't grow. And just recently, single molecular layers were observed nucleating on both the basal and the prism faces. So here's the basal face. You can see these edges, the layers moving across. On the prism face, they're nucleating a little bit faster. This is at -15. You can see some layers merging, coming from two spots. Now, one thing about these observations is that they're done in a pure vapor on a relatively large ice surface, not on snow crystals in air. Now, with a crystal in air, the nucleation will always be at the same point, generally the corner. Still, this is a very impressive experimental observation. Next, we examine branching and side branching.